back, and so I've written up here at the top the two concepts that we've talked about so far. So we've talked about what do we mean by linear distance. So the distance that something travels sideways or up and down or even like this. So a linear distance is going to be given by the letter R and is measured in meters. And then you should know what do we mean by an angle through which something rotates. So the angle is given by this letter here, which is called theta, and its official metric unit is the radian, where if you go around in a complete circle, that's 360 degrees or 2 pi radians. Now we want to talk about what do we mean by velocity. So just as there is a translational and a rotational version of the distance that something moves through, we can do the same thing for velocity. So velocity is going to be given by the letter V. So this is linear velocity. The velocity something has if it's going sideways or up and down. And you can see that its units are going to be in meters per second. And then we even had a formula for how to calculate the average speed of an object. So the average speed or the average velocity was equal to the distance it traveled in a certain amount of time. And so meters per second is the units that goes with it. So we've already discussed that in previous labs. So now we're going to go on to rotational velocity or rotational speed. Now there is a difference between speed and velocity. Speed is a scalar, it just is a number, and velocity is a vector. It has both a number and a direction associated with it, but not important to us. So I tend to use the words speed and velocity interchangeably. So this is going to be rotational velocity, rotational speed, or you could say angular velocity, angular speed. It's all the same, okay? So don't get hung up on the words that I'm using here. Now, it does have a different letter. So this is called omega, and it's a good thing to make it like that and not to make it like this, because this means work, and then this one up here, that's kind of the Greek letter for it. So that's called omega. And then, just like we could do it for linear velocity, we could do it for angular velocity. So omega, angular velocity, is going to be angular distance. So instead of r, which was linear distance, we want angular distance. So that's going to be theta and then divided by t. And so I didn't put the word average in there, but these are kind of like the definitions of what these concepts are. And now let's look at the units. So this is radians, this is seconds, so it's going to be in radians per second. So then that's going to be angular velocity. Now it says to click on the green plus symbol to turn on the angular velocity graph. So we're going to go back to this, and currently we just have the angular distance graph, but now we're going to click on this button right here. So click on the plus one, and now we've got two graphs. So this is your angular distance, theta, and then this is your angular velocity right here. And then you can see it gives you a readout. So the angular velocity is this number in radians per second. And then this is telling you, so the purple line here is telling you how much time has elapsed. So you should be able to read that number, how much time has gone by. And then take a look at this graph. Do you notice anything peculiar about the shape? is horizontal. Now that should be setting off alarm bells in your head, okay? Anytime on a graph that something is a straight line, something is constant. Something is not changing, okay? What is not changing in this graph here? Since it's a straight line, okay, it's telling us in this case that there is no the velocity is constant. It's not changing. So as we're going from here up to here, it was a constant velocity. Okay, so that's what this thing is trying to tell you. Now it's kind of hard to read it. Okay, now we know that it's this number right here, but if you wanted to read it off the graph, do you see these buttons over here? So you got a minus button and a plus button, and then an arrow that points up and down. So that if you click on this button, you see that you can expand the graph so that you can read whatever it says. And then you can also make it get smaller if you want. What do you think this one does? So this one has a plus minus, but it's going sideways. So that's going to expand your graph like this. So useful buttons if you need them, but just remember that they're there in case you do. Okay, let's go back to the lab now. And it says that we have now clicked on the green plus symbol to turn on the angular velocity graph. Notice how much time has elapsed from the graph. Okay, now using your value for the angle from the previous part in radians, calculate the angular velocity using this equation. So you know the angle through which it rotated. Okay, so you go back to the previous one and write that number in radians in this box. Okay, measured time elapsed, so you can get that from the graph. Put that in here. Okay, then calculate the angular velocity omega using this. Put that here. Okay, and then the measured angular velocity, you can get that off the graph. So if we go back to here, it's telling you what omega is. So that's this number. So you're going to compare the number that you calculated with this number right here, and then you're going to put that in here. Okay, our last thing that we need to talk about for this part of the lab is what do we mean by acceleration. So we've already talked about in previous labs what is linear acceleration. So that's given by the letter A for acceleration, and its units were meters per second squared. So that's the acceleration that something has when it's falling or when it's going sideways. So do you figure that they have a version of this for rotational systems? And yes, they do. So if we keep going down, we have alpha. So alpha is the Greek letter A, and it is going to be how fast is the speed changing. So let's look at the formula here. So alpha is going to be equal to the change, triangle, the change in omega over t. So when it came to linear acceleration, so let's go back to here, there was a formula for linear acceleration, and acceleration changes your speed over time. And so a linear acceleration changes your linear speed. It makes you go faster or it makes you go slower, depending on the sign. And now this is angular acceleration, and it changes your angular speed, where angular speed was the omega thing up here, and it's over time. So we could actually calculate it, but you notice I'm not having you calculate it. So you've done enough work, you did the theta thing, you did the omega thing, you don't have to do the alpha thing. But let's look at the units. So the units are going to be in radians per second squared. And so the reason for that is this is in radians per second, so that's omega, per second. So when you put the 2 seconds together, you get radians per second squared. Now it says to click on the green plus symbol to show the angular acceleration graph. So now finally we're ready to click this bottom one, and so there's all 3 of them. So that we've got the angular position, we have the angular velocity, and now we have the angular acceleration. And look at the graph. So do you see that the graph is horizontal? So it's a straight line, so that means something is not changing, and it is actually horizontal. Now this one up here is also going to be horizontal. So this was a constant velocity of this number here as it rotated through. So this was a horizontal line. Sometimes it's hard to tell whether it's horizontal or whether it's tilting, and so the way to do that is to expand the graph over here, just to that will make it more obvious if it really is horizontal or if it's at an angle. This one is also horizontal. So this one is telling me that the acceleration is not changing, and as a matter of fact, look at the number. Do you see that the acceleration is 0? This is pretty important. So if we go back to here, okay, what is the value of the angular acceleration, and explain why? So I'm not going to do it. So you should know that the angular acceleration is 0, and then use this formula here to explain to me why is the angular acceleration 0. Okay, now it says to increase the rotational acceleration to about 1, or pick any number that you want. So it's up to you. So it's just like Bob Ross. So you make your tree any way that you want on your art. If you don't have any idea what I'm talking about, look up Bob Ross. He always used to say that when he was painting. Make it your little tree. So you make this number here anything that you want, 1, and then run the simulation and observe what happens to the ladybug. Now you might need to let it run for 30 seconds or a minute to be able to tell what's happening, but go ahead and do that. And it says just to describe the motion of the turntable or the motion of the ladybug. So what is happening to the turntable if the acceleration is not 0? All right, let's take a break. And when we come back, we are going to talk about what's the connection between angular velocity and linear velocity.